Hello everyone, welcome to Machine Organization and Programming. Today we're going to be talking about dynamic memory allocation. This is reserving memory on the heap. So we're going to begin with an overview of the whole memory structure, how it's all laid out, a little introduction to specifically variables that are stored on the stack and how stack frames are arranged as we call functions. Then we'll dive into the details of dynamic memory allocation, talking about the heap, and then specifically about the command Malloc and its cousins, and follow up with some examples, and then all of the things that go horribly wrong when we as programmers make mistakes. All right, so first I just want to start with what's going on in the entire memory address space. So when you start a program, this is running, the operating system is going to give you a bunch of memory addresses that you are allowed to use. We'll talk later about how it takes care of all those details, but here's the idea. In that address space, we've got sections for a bunch of different things. So first thing that happens, address 0 is reserved. We talked about how that's reserved for, we use null for pointers, and because that address space is reserved, if we try and use a pointer that we haven't assigned a real value yet, it'll crash. So the operating system takes care of this. If we ever try and address the reserved 0 address, it's going to crash. All right, then when we load a program, it's got some code there, and those instructions are stored in this memory. And generally they appear at the top near the low numbers. I've got the big numbers down at the bottom, so it goes from 0 all the way to some maximum, however many bits I get. Then following that is the data section. These are going to be things that are constant in the code. Not the pre-compiler defined, hash-defined things. Those are replaced, but these are going to be like strings that we've assigned a value. They're going to be in this data space. Following that is the heap. The heap section is where we're going to have dynamically allocated memory. So if I want to just reserve a big chunk of memory and control it myself, that will happen on the heap. And then finally, beginning at the very bottom of the address space and moving up, we have the stack. And the stack is going to be the memory that holds the local variable. Actually, hold on, I've got a, next couple slides. The stack holds the local variables, the return address, the return value, and parameters, stuff like that. I'm going to picture that in a second. So I want to point out, though, that one of the reasons that this is really important is there's a maximum stack size. I'll show you how to actually get that when I switch over to demo mode, but it's not very big. The heap is much larger and is a much better place to store large data structures. Okay, so I've moved the stack over. The first thing that happens when you start a program is in C there's always a main function, and that main function gets pushed onto the stack. I've broken this a little more with other function calls, but somewhere in main, if there's a function call, it's going to push a new stack frame onto the stack, and the stack is going to grow this way. So we'll get another box here for another function. In this case, I've called it foo because that's what you name generic functions that you don't have a good name for in computer programming. So anyway, we push foo onto the stack. Now let's take a little bit about a look at what's going on inside of each of these stack frames. So we have to store a number of things in a stack frame. First, the return value. This is the instruction where we jump back to. So somewhere in main, there's a line that says foo, and the address of the instruction immediately following that function call is what's right here in the return value. So that way, when the program is done executing the code, it knows where to go. And that code is up here somewhere in this code block. So the return address, oh man, I'm talking about the wrong one. Return address will be an instruction somewhere in the code section. The return value is if foo returns a value like int foo, some parameters, whatever. That integer value is going to be the return value. And it's reserved some space right here so that it's going to be the very next thing on the stack after we return to main. Okay, then it needs to reserve some space for some parameters. So if in this parameter list there was an int n and an array or something, it saves space for all of those. And then finally, any local variables that are used are stored following the parameters. The very top of the whatever we've used for memory is the stack pointer, and that's going to be where we store the next thing. So if I have like a for loop or something inside my function foo, and my for loop says int I equals 3, it's going to grab the next memory space available up here, add that local variable I, And then as soon as that scope ends, the stack pointer is going to move back down, and we no longer have access to I. Okay, I've drawn this with some extra space because it doesn't actually know how much space it'll need if we use a variable length array, which I'll talk about later. I'm going to do some examples as a way to actually experiment with the stack size. Okay, so if somewhere in foo, I call another function, bar, the other name we use for functions that we don't have good names for, that will add one more frame to the stack, another stack frame. That's again going to begin, the very first thing is the return value for bar. So if bar returns an integer, there'll be an int in front of its declaration. We'll have that return value stored right here. Then the return address will be an instruction somewhere up in the code, the parameters for bar, and then the local variables we use. And again, there's space for variable length arrays or something like that. The stack pointer, again, will now point to the very top level of the stack. And there's a frame pointer, I didn't draw it in, that returns to the top of the previous function foo. So right there at the top of that, there'll be a frame pointer. And then when we're all done with the function, it gets nuked. So I've got the big X right here. What happens is everything up here above that is just gone. We no longer have access to it. And the return value, whatever is in these next memory locations right after the top of foo, gets placed in the whatever parameter, whichever local variable is, like if it's int n equals bar, it gets copied right there as the last step of what happens when we execute that code. All right, so when this is all done, there's a big giant red X that I didn't draw that nukes everything above these local variables for foo. All of this is gone. Yep, there's bar is gone. And then when we reach the end of foo, there's a return statement. Foo is gone, and we lose access to all of the local variables and parameters from foo. And finally, then we're just left with main. And when main ends, the whole program ends. All right, guys, I just jumped over onto CSL machine and wrote a little bit of code to get us started with a quick demo. Right here, I've got a function called reverse.c, a file called reverse.c. Please, at this point, go to the code directory on Canvas, download this one, put it over on the CSL machine of your choice, and follow along. Oops, I'm in the wrong. There we go. Focus. All right, so all this does at this point is, here, we've got a function print array that's going to print out an array. In main, I'm declaring an array with 5 elements, 1, 2, 3, 4, 5, and then I'm calling print array. I've hard-coded the 5. I'm going to use 5 elements for this entire demo. This is bad practice. Don't do it. But for the demo, it's going to be fine. So print array, all that does is take an array. In this case, I'm using the pointer version, *A. This could easily be done also with the array notation version. And then I'm just going to go through for I equals 0, less than 5, increment, and just print out the elements of that array. And then finally, after we printed out all 5 elements, we'll put a new line in there. So let me just go make sure this actually works. So I made one tiny change. Let's see here, we will run that, and then we'll run the code. And all it does is print out the numbers 1, 2, 3, 4, 5. Now I named it reverse because one of the things that I want to do with this is go ahead and reverse that array. But what I'd like to do is not just change the order in place. I want to create an entirely new array. So I'm going to go up here and write a new function. This function is going to return an array. And the way we do that in C is to return a pointer to that array. Now I don't need a name for that right here. But int star creates a pointer. That's my return value. So just like this one says void, or if I had something that returns an int, I would use int. Int star is a type. I'm going to name this reverse. And then it's going to take an array. So int a, we'll do that notion this time. And then down at the bottom, here in main, let's actually call it. So what I'll do is I'll have a pointer to an int. This will be my array. And that's going to be returned by the function reverse. And we'll just pass a to that. Okay, then we'll print it out. Okay, next up. Let's see. When I write the function definition, it returns a pointer. I can spell really. Reverse int a. All right. Now what I'd like you guys to do at this point is see if you can figure out how to do this. Go ahead, follow your gut instinct. What would you do in Java? Go ahead and write this function, and then pause the video, go take 5 minutes and come, just give this some thought as to how you would approach this problem. And then in a second, I'll be right back, and I'll write my version and talk about the problems with the common way to do this. All right, so ready, set, go. All right, guys, I'm back. Let me go ahead and write down my version. So the first thing we're going to do is we're going to create a new array to hold these values. So the way I'm going to do this, int, call it R for result. It's going to have 5 members in it. So there we go. I've created an array. Now I need some counters. I is equal to 0, j equals, let's go with 4. There we go. And now, while I is less than 5, I less than 5, all I'm going to do is say that R of I equals A of j. Okay. Now the next time through this loop, I need to increment I, so throw in a plus plus. So I will go from 0 to 1 to 2 to 3 as it goes through. I'll put it until it reaches 5, then I'll exit the loop. Now j is going to start at 4. And then it needs to go down 1. So it goes 4, 3, 2, 1. So we'll do j minus minus right there. That's all I need to reverse that loop. And then the last thing I need to return my pointer. And R is a pointer. Okay, so this is my gut instinct says this is how I would do it if we're not aware of some of these issues that come up with the stack. So let me go and run this, and then we'll talk about why this is going to fail. So we'll write and save. We'll compile it. Oh, let's see. I forgot 1 semicolon. That's what I want. Where was that? There it is, line 11. Let's try this again. Okay, it actually gives me a warning that the function is returning the address of a local variable. So if you guys remember over here when I was doing the PowerPoint presentation, over here, I'm calling. Let's go with this one. I'm calling a function. This is my reverse function. I store some space for return value. That's a pointer, so 4 bytes there. The return address as an instruction in memory up here in the code. I've got some parameters. That would be the variable that I input, the A variable. And then local variables, I've created a new array, R, to hold the result that I'm going to return. And that's using this space right here. Now, as soon as that function ends, right here, I nuke my function. So reverse is just gone, and all that memory is reclaimed. It's no longer available, and the operating system recognizes that that space is no longer good. And C gives me a warning about that. There's my warning. Warning function returns the address of a local variable. That's bad. This should not work. It might though. Sometimes it does. Okay, no, it did not work. Segmentation fault. So it's trying to access memory outside of the range that it's allowed to access. So something that's no longer on the stack. It knows where the stack pointer is. It knows where the bottom of the heap is. None of the stuff in between is accessible. Okay, so this is good. Segmentation faults, when it crashes, those are good. This is so much better than those weird undefined errors that pop up and you just cannot track down. I got a warning that tells me exactly where things are going wrong. All right, so let me show you guys how to fix this. All right, so we'll just jump back over here into Vim, and then I'm going to comment out this version. Well, I'm going to make a copy of it, but I'm going to leave this here so you guys can see it when you download the complete version from the lecture. So let's see here. We'll go to block mode. We'll get, I don't want block mode. I want line mode. And then we'll just copy those, go down here, and paste them. All right, now I'm going to comment this one out, and I'm going to do it with the //*/, and then we'll go with bad version. And then this means a // that way. Okay, now to turn this off, what am I doing? // star. There we go. Messed up my comment switch. All right, so now I've got the real version here. I still want this same function prototype. I should be able to create an array, return it, but have it reversed. The only problem I have here is this line right here. I'm creating an array on the stack in that local variable space reserved for local variable address space. So I'm going to get rid of this line right here. So get rid of that line. And then what I really want to do is create an array somewhere else in memory, not on the stack. And the place reserved for that, for creating dynamically allocated memory, is the heap. So this is where I'm going to create all of the memory right up here. This space right here is reserved for when I want to create a new array in a function, or reserve some memory for whatever I want, and not have it get nuked when the function ends. That's the whole purpose of the heap. All right, let me jump back to Putty. Here we go. So the way I reserve some space on the heap is with a function called Malloc. So here's the idea. There it is, Malloc. This is just a function that reserves a bunch of memory. It's very straightforward. It returns a pointer to that space in memory. So this is going to be pointer to an integer. Gets returned by Malloc. And Malloc only takes one parameter. That's going to be how much space I want. So in this case, I need an array that reserves space for 5 integers. Now, the input value here is actually in bytes. So if I just put in 5, that will reserve 5 bytes. On this machine with 4-byte integers, that's enough for 1 1/4 integers. So pretty much always we use this sort of format for this, size of int. So that way I know it's 4 bytes on this machine, and I could put in 4 if I wanted to hard code this, but then it would not be good on any other machine that used more than 4 bytes for integers. And all that C does is guarantee that the minimum size for an integer is 4, but it could be bigger. All right, let's see, then I need a semicolon. There we go, size of, nope, I need another parenthesis too. Okay, size of gets parentheses, Malloc gets parentheses. Okay, now this will reserve some space, and then I'll return a pointer to it. Now, there's one more thing I need to do. In C, you are entirely responsible for your own memory management. So if I reserve some space, at the end of my program, I need to free that space. So I'm going to go up here to the bottom line of my main function. Oh, I forgot my return value too. All right, so hold on. Little typo there. Forgot that. Okay, put that in. Last thing I need to do here is free that memory that I reserved. And to do that, it's P has a pointer to that memory. So all I need to do is free P, and it will return that to the operating system, so it's now available for other use. Okay, I'm going to compile this and make sure I didn't make any weird typos. Lots of weird stuff. Hold on. Let's see that without warning. Implicit declaration of function free incompatible. Oh, I forgot to include standard lib. stdlib. All right, so let's go add that. My fault. There we go. Oh, perfect. Now all those warnings went away. It no longer gives me the warning about returning a pointer to a local variable. Fixed the fact that Malloc and free were not available. Okay, so now let's go ahead and run this and just make sure that it really works. Oh, excellent. Check that out, guys. So here's my original array, 1, 2, 3, 4, 5. That's A. And then I've created a new array in my function reverse and returned a pointer to that, 5, 4, 3, 2, 1. All right, I just want to pop back over here and take a look at this memory address space again. So when we called reverse, and gave it the local variable A from main, it returned a pointer to an integer. We called that P. This actually would have been in main, so I've got an extra line right there. Sorry about that. I'll fix it for next year. Okay, so when we called Malloc, what that does is it reserves some memory space up here on the heap, 5, 4, 3, 2, 1. And this is now under our control. It's not going to get nuked when the stack frame ends. And somewhere in memory, it's created a pointer to this space that it reserved and returned that. So over here, it got stored in p star, and then I used it. So p star actually includes the address that was returned by Malloc. So in that function, it was called R. I returned it. I renamed it P in main. So, and one other little detail here, when we're done, we called free to delete that. Now, it's got to keep track of how much memory do I need to return to the operating system. And that size is usually stored in the address right before the addresses that it's reserved for us. So there are a lot of issues because C does not stop you from accessing memory outside of the actual range of your array. There's no bounds checking. It's actually pretty easy to overwrite this if you accidentally, count down to -1. So this is the index before. It doesn't have to be there, but typically is. Or if you have a second array in memory and exceed the bounds, you'll be overwriting and then you exceed the bounds for this one, 543210. You'll be overwriting the size of that array. And all of these little things, the out-of-bounds errors, lead to huge problems when we're working with memory that we have taken control of. We're in charge of that. It's our job to not screw it up. And I was also going to mention that this malloc function is a lot like the new function in Java. Java uses new to create an object on the heap. It reserves memory for whatever object that is, an array, a tree map, something like that. Whatever, it's storing that on the heap. Okay, and then when we're all done with that, Java has a delete function, so new and delete are paired. When you're done with the object, you can delete it. Same way that free works here to say, okay, I'm freeing a pointer that goes to this spot. Look here to decide how much I'm returning, and then we're no longer using that. That's free. The operating system can reassign it as it wishes. All right, guys, next up, I've got another example here. Dynamic array 1. Go ahead, download this from the code section, pull it up, and follow along. The idea here is this is going to demonstrate that the stack is actually a very limited size. Okay, so I'm just going to run this dynamic. I'm going to switch focus back to Vim. No, back to CSL. Dynamic array 1 runs. All right. Dynamic array takes a number. Let's go with 5. Just to demo this, it's going to print out what num is, and then it's going to create an array of length 5 and initialize everything to 0. All right, let's take a look at the code. Vim. Okay, here we go. So including standard io.h because we'll print stuff, standard lib because we'll use malloc, and then we can see here in main, the very first thing, we're actually taking arguments from the command line, and it's verifying that there's exactly 2 of them. The first argument at index 0 will be the name of the program, and then the second argument will be how big the array we're going to make is. So, and if we screw that up, then we get this error message that I just showed you guys because I screwed it up, and it's telling me that I need to give it the number of elements. And then exit 1, I think I mentioned this last time, but exit is a lot like return, except that it is a system call instead of a function return. And when the system call runs, it doesn't matter how deep into the program we are. We could be in a function that called another function that called another function. It's just going to exit. The one here is an error code letting the operating system know that something went wrong. We can actually echo that error code to the console and see what it is. Maybe I'll demo that in a minute. Okay, so here's the idea, what the meat of this code is doing. So first, it's getting num from our GV from the first argument. Okay, so from at index 1. All right. So first one is the file name. No, the program name. Second one is this num that we put in as a user. A to I stands for Ascii to integer conversion. So this is just going to take some string as an input in Ascii and convert it into an integer. So we'll assign that to an int. This is a decent way to do it here. There are better ways, but this gets the job done. But it doesn't deal with a lot of the weird situations that might come up. Okay, anyway, then we're just going to print that number out to make sure we didn't screw up. Okay, we can see that it's there. And then we're going to create what's known as a variable length array, VLA, just like this. So up until about C99, exactly C99, during that revision, you had to use constant numbers in order to declare an array. So either a literal, like I could stick the number 5 in, or if I were using a variable, it had to be declared const so that we couldn't change it. That way, the compiler would know ahead of time exactly how much space to reserve. C99 introduced the idea of variable length arrays where I can do this. I can give it a variable. This is actually user input. The code has no way to know how big the array is ahead of time. There are some issues with efficiency doing this, but just assume that it works for right now. Okay, then after we've created this array, this code right here just initializes it. It goes from 1 to num and sticks the value 0 in everything. And following that, it prints it out. All right, so let's go back, and I want to just play with it just as it is. So, dynamic array, we did 5, let's do 10. Okay, works just fine. I'm getting zeros everywhere. Let's do 100. Also works just fine. 1,000? 10,000? That was even pretty fast. 100,000. Not bad, okay. 1,000,000. All right, I cut the video so you didn't have to watch all that scroll by. But yeah, even 1,000,000 worked. Let's try it with 10 million. There we go, 10 million. Okay, so 10 million, and we get this segmentation fault. So this is, we've reached the limit of the memory that's available on the stack. So it's actually not very much. It can't even hold, well, 10 million, that's 40 million bytes. So about 40 megabytes, and it's done. Okay, so not a lot of memory there. The heap, I mean, my computer here is sitting here with 16 gigabytes of memory. I've got tons of memory available, but just not very much of it's on the stack. All right, let me see. Let me look up that command. There it is. Okay, we can actually print out a bunch of stats about the limitations of what we're using. The command for that is just a system call. We can system program. We can call it right from the command line. It stands for user limit, and -a gives me all of them that are available from this program. If we take a look here, let's see here. So core file size in blocks, data segment, scheduling, priority. Where is it? Stack size right here. Okay, this is telling me that my stack size is limited to, let's see, 8192. This is kilobytes. So I want to multiply that by 1024, which is about 1,000. So that's about 8 million. Maybe a little more than 8 million bytes are available in the stack. So some other interesting things here too. All right. But that's what I want to talk about for right now. Let's go back and take a look at that code one more time. All right, so back looking at the code. Now, what I want to do is take a look at this section right here where I'm initializing everything to 0. And I'm just going to comment this out and take a look at how it performs differently. So Control-V, JJ, Shift-I, comment. And that'll put him in, that's the block mode, visual block. Okay, so now it's going to create the array right here in line 14, and then we're just going to print it out without ever initializing it. So write and save, RG, there it is, compile dynamic array, and then dynamic array 1. Oops, I forgot to give it how many elements. Let's just do, I don't know, how many do you think will fit on the screen? 20? Oops, that's 120. All right, well, we got some on the screen. Now, before we had initialized everything to 0, and I just like to highlight that there's a lot of garbage in here. Everything is pretty much initialized to some sort of random number. That's likely because as a user, I've been using the machine for quite a while today, actually, and yesterday. I don't ever think I logged out. And so I've been using this memory, and I put lots of different values in it. Sometimes, and I forget which system does which, but Windows does one thing, Mac does another. But as part of their security, they will, when you log in as a user, they'll initialize all of the memory to 0. So that you can't actually steal like stuff from whoever was logged in before you by just being able to read the memory and see what they were doing. So a lot of times when you log in, you will see that everything has been initialized to 0. And by making the assumption that it's already been initialized to 0, you can be in big trouble later when you find out that it's actually, 80 million instead of 0 like you expected. Or even something negative if you expected, a positive number. So Ascii does not take any extra effort to do anything for you. If you want it done, you've got to do it yourself. It doesn't initialize anything. It doesn't check bounds. Those are your responsibilities as a programmer. And the number one reason for that is speed. Alright guys, I'm back, and I've gone ahead and made just a few changes to that code we were just looking at. And I renamed it Dynamic Array 2. So when you download it, this will be the file you're looking at. So from here, let me just walk through what this does. So I've got my in main, I'm grabbing arguments from the user, and again this is just going to be the number of elements, and turn that back into a string into a number. And then instead of just creating a variable length array, we're actually going to use Malloc and create an array on the heap. This is the best way to do this. So Malloc, as I was discussing earlier, takes the number of elements in the array and the size, because it really only takes one argument, just the number of bytes, and I'm doing some math here to get the exact number of bytes I need for this size array. And it returns a pointer. Now, I think I mentioned before that using pointers that have been not allocated correctly can be very bad. So the thing we're going to do, if Malloc fails, for example, if the heap is full and there's not enough memory left, could be working on a small embedded device of some kind, and it might just not have very much memory. We need to make sure that it actually succeeded. So Malloc returns a null pointer if there's not enough memory or something else goes wrong. So if a is equal to null, then we're going to say, whoa, something went wrong, memory failed, and we're going to exit immediately so that we know that there was a problem. So from now on, I didn't do that the first time when I was just doing the quick demo earlier. We need something like this. We need to verify that every Malloc operation succeeds. And then we're just going to go through and initialize them all to 0. Actually, we did 0 before. Let's change that to I. That way there'll be 1, 2, 3, 4, 5, and we can see what's going on. And then we're going to print them out. Finally, because we're now done with that pointer to that memory, we're going to go ahead and free it and release it. Return it to the operating system. That's not strictly necessary because this is the end of the program, and when the program ends, the memory is also returned. But this is good practice, and I'm going to highly encourage you guys. I'm going to require that you guys free up all your memory when you're done. But so imagine you had like a program that's running for a very long time, like a web server or something. If you forgot to free memory in a function call, it would sort of just use up more and more and more memory that was reserved and then not available. All right, let me go run this and make sure everyone can see what it does. So I made that one change. We'll save it. We will run this again. So I haven't actually compiled this yet. So I'm calling it Dynamic Array 2. And then Dynamic Array 2. It takes a number. We'll just do 5. So it should print out that array now. So A of 0 is 0, A of 1 is 1, and so on. Looks like it's working. 0 through 4. Okay. Dynamic Array 2.c. So the next thing I want to do, a dynamic memory allocation is frequently used to create dynamically sized arrays. Suppose that I start doing some work, I've created an array, and I suddenly find that I want to add more elements to that array. I need to make it bigger. So what I'm going to do here is just write some code that will take this array and double the size of it. Okay, so we'll just go ahead and do that right here. Let's see here. I'll check that out. Automatically filled in. Double the size of the array. Okay, excellent. So something that just kind of looks like it might be a good idea at first, and we'll talk about why this is bad in a second. We'll just get a new array. 2 times num. There we go. Now it's twice as big, and of course we need to multiply by size of an int. There we go. Now, of course, it's always good practice to make sure that I just malloc something that it actually worked. Let me copy this. Visual. Copy. Paste. There we go. So now if A is null, that means it failed, and it'll exit. All right. Next, let's see. Let's go ahead and print out the array again. So let me just grab these lines right here. Whoops, one more. Copy those. Paste them. There we go. And now we actually made the array twice as big. So I'm going to make one more little change right here and just print all the way up to twice as big. Right, and save this. And then I need to compile it and see where I made all my mistakes. Okay, we'll do 5 elements again. All right, excellent. So 0, 1, 2, 3, 4. That's my original array. and now I've got all these zeros in here. Alright, so it's twice as big, definitely it's printing something out. Let's go take a look at the code. There's two real problems right here that we're about to run into. So we'll go back over here. So first, this Malloc just grabbed an entirely separate region of memory. It's twice as big, but it doesn't overlap this first one. And that's why the numbers were all 0. There's also no guarantee that those numbers will be 0. We did nothing to initialize them. So it's just weird random luck that I hadn't used that memory before. They're probably initialized to 0 by the operating system when I logged into the machine. And just hadn't happened to use that spot yet. Alright, so, yep, when I printed out the new A. So the other problem is up here at the very top, this Malloc, the very first one, reserved space for 5 integers. And that's a pointer there. So in memory, like the one memory, the spot right before this is how many bytes that are belong to this block that we reserved. When we free it, it just goes back one spot, reads how many, and then frees up all 20 bytes. Then when we did this Malloc, A is already a pointer, I didn't need to do the int star A. It grabbed 40 bytes of memory to hold 10 integers, but in a different spot. And I no longer have access to the pointer that was pointing to this memory up here. This now points somewhere else. So I don't actually have a pointer anymore to this memory. So I can't go back and free it. I can't release it. This is a memory leak when I do something like this. This memory will be forever allocated, and I can't return it and reuse it. This free down at the bottom right here will free this array of 40 bytes. And 40 bytes doesn't seem like that much. 20 bytes is even smaller. Sure, we can afford to lose that, right? The problem is if the code runs for a very long time, and this happens over and over and over again, like a web server, or actually I guess my favorite story, and I'll go ahead, this is a side, if you want you can skip ahead a minute, but the guy who used to teach graphics here, he's moved on, he's at a different school now, would have students write a graphic program that just did an animation. It was a train that went around a track over and over like a roller coaster, so you would do this animation for your final project. And then when you turned it in, you just had to go to his office and run the code, and he'd watch it. But then he would make small talk. And he would just let your train go around the track over and over and over. In computer graphics, all the little triangles needed to describe how things look do take up a lot of memory. And if you had any mistakes in your code, any memory leaks, during, a 20-minute conversation, your laptop would run out of memory and it would crash. And then he would try and get you to explain why your code crashed. So, all right, that's the end of the story. It's important to free all of the memory you use. All right, so this is not a good way to do this. I'm going to actually put a little note right here. This is bad. Okay, and then I'm going to comment this out. Let's see, how do we want to do that? Oh, the other thing, because I've lost that pointer to the initial... Here, this is where I initialized everything, right here. I no longer have a pointer. A doesn't point to the right spot, so I can't go back and copy all of the old data that was there and just add new stuff. I've just completely lost all of my old data. I now have an array that's twice as big. So I guess this really has all kinds of problems. All right, so get rid of that. Control V. All right, there we go. That is now gone. So we need a better way to do this. So I was just thinking about this. What I'd like you guys to do is go ahead and pause the video and see if you can write some code that does this a better way. The secret is that we don't want to allocate the new memory to A like we did right here. We need a new pointer. And then we can copy the data from A over to the new pointer. In my demo, I'm going to call it P, so if you want to use the same number, that'd be great. And then we can free A when we're all done with it. And if we want, if we still want it to be named A, we can actually, after we do that, reassign P to A. So pause the video, go write this, see how it looks, and then you can come back and look at my solution. Actually, I don't think this will take very long. I'll just go ahead and write it right here on camera. Better way to... All right, better way to do this. Okay, so first up, I'm going to need a brand new pointer. I'm going to call it P, and then I'm going to malloc. This is actually, I need the same thing right here. So we'll just copy the rest of that line, paste that in right there. So I still need the same amount. I need double the amount of space. And then I need to verify that it still works. So just good practice. I'm going to enter, whoops. Oh dear. Like, what am I doing? Stopped. All right, hold on. I'm going to pause this. All right, I didn't think it'd take very long, but it crashed on me. I lost all those changes I made since here. Anyway, I went back, I added the comment, this is the bad way, and some extra information. We can't copy the old data, and we can't free the memory because we've lost that pointer. Okay, next up. Start here, Control V. Scroll, nope, there's the problem. I want Shift V for line mode, copy that. Oops, not right there. Undo. Paste that, and then this is the bad one. I'm going to comment this out. There we go. We'll make that line up a little better too. And then down here, the only real change I need to make right here is I want to change the name of my pointer from A to, I'm going to use, I think I said I was going to use P. So then I will be grabbing some more memory allocate 2 times the number that we've had before, and then if P is null, that's bad. Memory allocation failed. We'll exit. And now from here, I can do a couple things. I can I still have access to the old A, so I can copy the data over. So for int I equals 0, I less than num, I plus plus, and then we'll just say that P of I, and remember pointers can be accessed just like arrays, is equal to A of I. So that'll copy this data over for the first num members of that set. And then once at this point I'm completely done with A. So I can free A. All right, perfect. And now I'm not going to change the code further. I'm doubling the size of A, so I can just say A is equal to P, and that will take the value of P, this is the memory location where the bigger array starts, and reassign it to the variable A. And now I can go ahead and print out A. And then when I'm all done, I'm going to free A again. And remember, it doesn't matter what I called it. I actually have 2 pointers that point to the exact same location, the start address of the bigger array. I could use P here. I could free P, or I could free A. Either one of them will work. So let me just write and quit. Then we will run this again. Oh, and I forgot. I missed a semicolon. Okay, timeout. Where was it? Right there. And now we can run this again. Dynamic array 2, and we'll give it 5 elements again. So now we should see that we get 0, 1, 2, 3, 4. That was my original A up through there. And then I've doubled the size of the array, and I've got 0, 1, 2, 3, 4. All right. And again, these last 5 values in here, for 5 through 9, they started 0, but that's likely the operating system cleared the memory, so I couldn't spy on whoever was using the computer before me. But they are not allocated to 0 by C when we run the code. They're just left unallocated. All right. Part of the lecture I wanted to talk about was common errors using Malloc. And the one that just jumped into mind, I want to do this right now because I just had some code that would be a perfect example of this. This is error number 4, the double free. So let me jump back over to that code real quick. There we go. Oh yeah, and I made a copy. I'm looking at dynamic array 3 so that when I post this online, you guys can see this change I made. But right now it's also still in dynamic array 2. Okay, so down at the bottom here, I'm freeing, let's see, yep, right here. So at this point, I'm freeing A, and then I'm reassigning A, and I'm freeing A again. So this is that first block of memory with 5 elements. I totally free that, it's fine. I only had 1 pointer to it. This free, the pointer was reassigned to that block of 10 elements. So that's a different location of memory. I can completely do this again. They are different memory allocated read blocks by Malloc. The temptation is to do something like this too. Free P. Either one of these will work. A points to that block, P points to that block. They the exact same value in memory. However, doing both of them is bad. So once I've done this first one, free A, it traces to the first memory location, it goes back one to figure out how many to free up, and then frees them. They're available now, they can be reallocated to other things. This P right here, however, points to that exact same memory, but it's no longer allocated. So when I free it, it goes back one. This could be a completely different number because C is going to reuse that memory for us. And then it could just be a random piece of garbage. It could be an enormous number, and then it's just going to go back and free an enormous quantity of memory, and we're going to have all kinds of problems. These double free errors can be really deceptive, and they can be hard to track down. It generally results in what's known as indeterminate behavior. All right, quick vocab lesson. Let me pull up a web page real quick. All right, I do feel it's very important that I do my best to teach you guys all of the relevant vocabulary and how to pronounce words as to the best of my ability. So nasal demons are I can't even say it without laughing. When the compiler encounters a particular undefined construct, the quote from this particular user group was, "It is legal for it to make demons fly out of your nose." There's the quote right there, I highlighted it. The implication is that the compiler can choose some arbitrarily bizarre way to interpret your code without technically violating the standard. So if I'm got an undefined construct like a pointer to memory that's not been allocated or a double free or something like that, the compiler can do very weird, bizarre things. And someone followed up with and called this particular quote nasal demons, and it stuck. So anytime you see this, if you're looking for help online, they're referring to reference to memory that's not actually been allocated correctly, and weird things happen. This is also undefined behavior. All right, I thought I'd just skip ahead to this piece right here because I've been talking about initializing the memory a little bit and how C does not do that for us. So this is the man page for Malloc. I just pulled that up. And right here we can see that Malloc returns a pointer. It's actually technically a void pointer. And when we assign it like int star equals Malloc, it changes that void pointer, which is a pointer to absolutely anything. They're just giving us a block of memory. We're telling it that we're going to be using that pointer as an int pointer. We could do it for whatever we want. Okay, then this one just takes a number of bytes. Size t is just a parameter used to, it's like a type def for int or long or something like that. I don't remember which one. But it means we're going to be giving it an integer. Okay, the one I wanted to talk about now is Calc. The C stands for contiguous allocation. This is the one that goes back and will initialize all of the members to 0. It actually takes different parameters. So again, size t is going to be some kind of integer. It takes the number of members and the size of those integers, and then it's going to multiply those together for us to figure out how many bytes to use. So let me go back and let's see here. Q to quit. There we go. And show what this would look like if I were to use this instead. So right here when here's a good example. When I'm calling Malloc, this is just going to be giving me a block of memory that's unallocated. It's not going to do anything. If I were to change this, so replace that with a C, I'm creating 2 times the number of elements. Then I need to replace the star with a comma. So this first argument will be the number of elements, and then I need to give it the size. So I'm still going to use size of int. It's just going to do the multiplication on the inside for me, so I need a comma to separate those. This is exactly what I would do. That's most minor of changes to the code. The downside is it's going to go ahead and do a giant loop that goes through and loops through all the data and sets it to 0. And the next thing I do is use a loop to go through and set it to what I really want it to. So my advice is if you don't need to use the Calc version, go with Malloc. If you know that this is going to be fine, you want it might save you a few lines of code where you do your copying. But in general, this is far less efficient than Malloc. All right, and while I've got the page for the Malloc manual open, I also want to introduce the idea of using this function right here, the realloc or reallocate. This is going to take 2 things. It's a lot like Malloc. The size is going to be the number of bytes we wish to allocate. So we'll need to use the number multiplied by size of int. And it also takes a pointer. This has to be a pointer that was previously allocated by Malloc. So it only works with malloc pointers. If I just create a generic pointer and pass it here, it will not work. So make sure that this is you're actually reallocating array. So this is a way to change the size of the array. Here, let me actually scroll down a little bit when you take a look at the directions. So it changes the size of the memory block pointed to by the pointer. So I pass in the pointer. It's basically going to take a malloc pointer, get a new pointer for us, reserve that much memory, copy over all of the data from the previous pointer, and then free it. So this does all of that work that I just did all in one line. So and there's another function too, that if I give it the value of 0 for the number of bytes, it returns a null pointer and is essentially the same thing as, equivalent to free pointer. So another way to do that. May save you some time if you can copy and paste the line rather than typing free, if you're that good at copy paste using terminal editors. Okay, so Q to quit. Let me put this in some code. So right here, let's see, where should we put it? Here, I'm creating P. We'll do it right here. So realloc. This is how much space I need. The pointer I wish to reallocate is A. And then if P is null, that means something went wrong. And now this copy is already going to be done for me. And A is already going to be freed. And did it return a pointer? I believe it did. I don't remember. Let me go take a look. All right, I just pulled this back up and looked at the return value for realloc. Let me go ahead. It's right here. This is the phrase I'm looking at. But I think it might be easier to read if I don't highlight it. So it's telling me that realloc returns a pointer to the newly allocated memory. And it's going to use the same pointer, the same memory, if there's enough non-allocated memory that it can just like say, okay, make the space bigger. And then it's going to use the same location, and it doesn't need to do any copying. So this will actually be faster using realloc than doing it the way I did, if there's memory that I can just, like, if it can just change the number of bytes reserved. And it's not going to fill in any of the things that's not reserved. It's just changing like that one number right in front of the array that's telling it how big the allocation is. And if it does need to move, if there's not enough room, it'll find new space in memory where there is enough contiguous bytes in a row for this, and it'll return a pointer to that new spot. So let me jump back over to my code. So quit, pull this back up again. So I was just reallocating, and instead of using P, I'm going to go with A. And then A failed if that happens. Okay, now this will take care of the copying for me. I no longer need to do this. And I don't want to do this yet. I don't want to do that anymore. I don't have a P. And then, let's see here. Yep, this should print out everything. And now I want a free A. I don't want a free P. So let me just make sure that I don't have any typos when I post this online. There we go. Yep, that should be good. And then 2.2. Oh, I forgot the, we'll go with 5 elements. Okay, excellent. 0, 1, 2, 3, 4. And then, oh, check this out. So I copied 0, 1, 2, 3, 4, just exactly like I wanted. And then the next 5 elements, 4 of them are 0, but this one is garbage. So I told you, it does not allocate. But I haven't really done very much on the heap yet, so I probably haven't seen a lot of, it was probably, all pre-allocated to 0 by the operating system. And this is the first example of something where it did not give me a 0. So excellent. I'm glad I was able to show that to you guys. All right, guys, for my last example, I'm going to be looking at creating a 2D array on the heap. In this example, we're going to be transposing an array. So go grab the transpose.c file from the code directory, download that, and follow along. Okay, so here's what it's going to do. It's going to be creating a 2-dimensional matrix with rows and columns, just like a matrix, and filling it in with the first row 1, 2, 3, the second row 4, 5, 6, and so on. And then, my formatting is wrong. Quick. Add those. There we go. Okay, so here's what we're doing. We're just going to go through all the rows and then all the columns. We'll print out everything in that row, and then we'll print a new line. And then it goes through and does the second row and the third row. and then finally ends with a new line so that all of my matrices are nicely spread out. So we'll save this, and then, if there it is, we'll compile. And it's transpose, and we'll just print this out. Okay, so we can see that I've got a matrix with elements 1, 2, and 3 in the first row, 4, 5, 6, 7, 8, 9. Now, if you guys remember a little bit from high school linear algebra, when we transpose a matrix, that's going to take the first row, and it becomes the first column. So I'll have 1 here, and then 2 here, and 3 here, and then it takes the second row and becomes the second column. So the 4, 5, and the 6, and then same deal, 7, 8, and 9. Okay, so let me pull this up again. There we go. So I'm going to just create a function transpose. It's going to take in this matrix A. So I need A, and that's A columns because I need to put in, here we'll just do both. Everything but the first. And this is an integer array, so I need that. And then there'll be a function here. I'm going to think a little carefully about what the return type is. It's going to be a two-dimensional matrix, so and a matrix of integers. So I need int, and it's a two-dimensional matrix of basically a pointer to pointers of rows. So I need the double star version. Let me pop over to PowerPoint and explain that real quick. Okay, so here's the idea. This is the matrix in memory that I'm going to end up with. So I'm going to have 1, 2, 3 in the first column, 4, 5, 6. And now each one of these rows is going to be an array of integers. Okay, so I'm going to allocate some memory on the heap to them, and that's going to be pointed to by a pointer. Okay, the second row here is going to get a pointer. The third row gets its own pointer. All right, each of these pointers I'm also going to store in an array. So I'll have a pointer to row 1, a pointer to row 2, and a pointer to row 3. And this array will get a pointer, and I'm going to call this one P when I get to the code, pointing to the very first element in this array. So I need 2 stars because I've got 2 levels of indirection, or 2 levels of pointers to get to this data right here. So if you get stuck trying to figure this out for two-dimensional array problems, it can be very useful to draw a picture like this and then just count the arrows. Okay, so let me pop back over to Vim, and we'll go ahead and write this. So let's see. First thing I need to do is create that array. So it's going to be a double star pointer, and I'm going to malloc that first. Let me point. So this array right here. First thing I'm going to do is create this array on the heap using malloc. So there we go, malloc, and I need, let's see, it's going to have rows, and then I need to give it how many bytes it needs. So size of, ooh, here's a question for you guys. What do I type next? What do I need the size of? Is it the size of an integer? No, it's actually the size of a pointer. And I'm going to definitely do it this way with int star, because the machine I compile this on, or the way that I compile, changes. I know that a pointer on a 32-bit machine, it takes up 32 bytes. A pointer on a 64-bit machine will take up 64 bytes. So I definitely need to be careful, and I'm going to use size of, because C knows how big pointers are. Okay, so this is going to get me those first 3 pointers. The next thing I need to do is for each one of these pointers, I've got an array now. This is going to be a pointer. I need to allocate some memory to hold that data. All right. So what does this look like? Oops, it wasn't in insert mode. There we go. So I need to go through all of the different rows. So for I equals 0, I less than rows, one for each of the rows, I plus plus. What I need to do is grab some more memory. I need to create another array. And the pointer that I'm going to assign this to is going to be P of I. So when I is 0, this will be grabbing the first element of this array. So what does this look like? So this one right here is a pointer, and because I'm using the bracket notation, oops, this is my pointer. I'm using the bracket notation. That gets me this element right here. It's already a pointer because of that second star, and I'm just going to use malloc to return my new memory to that pointer. Okay, so piece of cake. Already in editing mode. Yep. So p of I equals malloc. Oh, in this case, I'm making enough entries for the columns. So we'll do columns, and that's going to be times size of. Now, in this case, it's not a pointer anymore. The actual data values are kind of these numbers. So they're just going to be integers. So size of int. All right, that looks good. All right, so this, like these 3 lines here, will give me enough space to fill in. Check it out. To declare that array down here took that much space. So doing it on the stack was definitely easier, but on the heap, it gives me the ability to create this data structure in on the heap. All right, next thing I need to do is just fill this in. So for int I equals 0. All right, so no need to watch me finish writing all of this out. The only real thing we're doing here, we're iterating through all the rows, then through all the columns, and then we're indexing this. So the P matrix that I've created right here, row I, column J, is getting column J, row I. So I'm just switching these, and that's all I need for the transpose. Last thing I need to do, remember this function is returning a pointer to an int, which is P. So we return P. All right, perfect. Now to wrap this up, let's actually call the function. So I'm creating a new matrix. So int t, starter t, that should work, is equal to transpose of A. All right. Okay, so that should make this. Now let's just go ahead and print this out. I'm just going to copy and paste. Should be, whoops, it wasn't in command mode. Copy this, paste it. Whoops, I didn't mean to do that. Undo, down 1 line, paste it. Right there. And then instead of printing out A again, this is going to be my new matrix T. And the new matrix T. All right, let's go find all the mistakes I made. Oh, check that out. I didn't make any mistakes. All right, that can't possibly be real. Let's see if it produces the right answer. Oh, looking good. Okay, so here's my original matrix with 1, 2, and 3 in the first row. And then that new matrix, the transpose, has 1, 2, and 3 over here. All right, second to last thing that I want to talk about today is what's going on right here, this Pij. I've got this double pointer to an integer, P. I'm accessing it with index I and J right here. That works great. But I think this is the part that I really confused people on from the last lecture, where I was trying to talk about how C gets from that pointer to where it needs to go. Okay, so here's kind of the idea. I'm going to break this down into a number of steps, and we're going to actually address getting to element 1, 2. So row 1, column 2. That's all the way over on the right side. It would be the 6 would be that value of matrix A. Okay, so here's what's really happening. I'm going to break this down into a number of steps. So to get to this position right, oops, it's an 8. Row 2, row 1, column 2 is the row 0, row 1, row 2. So this to get to that 8 right there. First thing I need to do is get to this second row. And I've got the address of P. So this is the starting address. So when I follow this one with the star, okay, I need to add 1 to that to get to this position right here. So let me go put that in some code. Now when I wanted this one, okay, so P plus 1, and then I want to dereference that with the star. There we go, something like this. Okay, that's going to follow my pointer P and add 1 to it, and then dereference it. So that gets me a pointer to the first row. Let me point to this one more time. So P plus 1 gets me to this position right here. It's basically taking an address that's in here, because P is an address, and incrementing it. So now I'm at this address and dereferencing it. So that will give me this array over here. Okay, next thing I'm going to do is I now have the address of that row. I want to move over 2 positions on that row. So let's see. I want to move 2 positions to the right, and then I need to dereference this to get to that actual data that's in there. So I'm going to just put some parentheses around this, and this should be adequate to get me that 8. All right, just to show you guys, I'm going to go ahead, copy this line right here. I'm going to put this in my loop. Right there, and replace the Pij. So this was the work I did to get there. I'm going to go ahead and leave this in as a comment. There we go. So there we go, that's how I got there. Now, because I'm putting this in the loop, my 1 here was the row number, so that should be I. And this 2 here was J. All right, did I do that right? Let's give this a try and see if I made any mistakes. Oops, I've left off the equals A, J, I. Okay, let's see if there's more mistakes. Looks good so far. Transpose right there. Okay, sweet. It works 1, 2, 3, 4, 5, 6 in columns. All right, so the last thing we're going to need to do now is talk about freeing this memory. So I jumped back into PowerPoint here. If I were to just say free P, all that's going to do is free this particular array. I'm still going to have this, this, and this all reserved out in memory somewhere. So I'm going to need to go through and loop through all of these, iterate through them, and free this pointer, and this pointer. So good way to think about this is that for every arrow you have, we're going to need 1 free statement. And 3 of these will be in a loop to just make it easy, and then we'll have that final free at the end to get rid of P. So let me go ahead and demo that real quick. I'll jump back over to Vim. This actually would be a good spot if you want to challenge yourself to push pause, write this code yourself, and then come back and see if you got it right. So in this case, in this function, I was creating P, and then I passed it to T. So what I really need to free here is T. So I'm going to use a loop to start off with. So for int I equals 0, I less than, I had 1 pointer for every row, so rows I plus plus. There's my loop. What I want to do is free, and this is going to be T of I. Okay, and once that's done, I've now freed all 3 rows, free, and we'll free T. And that will clear up the array with the pointers to those rows. So that's all I need to do at the end. It's just 3 lines. We'll clean that up a little bit. We'll save it, and we'll make sure that I didn't break anything before I post it online. Nope, looks like it still worked. All right, great. That's going to do it for me today.